Associate Professor in Architecture, in case you don't know me. And welcome to the third Champagne-funded architecture lecture on integrating innovative technology into design. And I'm very happy to announce that we have Tommaso Bitossi here from Vernacular, New York City. But he came to the US only 3-4 months ago. And he worked 6 years for Transsolar Stuttgart, which is the headquarters, founding location of this pretty important plant engineering firm. And I know colleagues from Transsolar for many years. We collaborate usually with them in our Berlin program. And they're pretty unique because they're engineers who really think with designers. And I think that's one of the major assets. I have Tommaso here, but a little bit about Tommaso himself. Also, he's originally an architect from Italy, and he allowed me to tell the story that he did not?
Yes, I did.
So he started as a civil engineer, he went over into architecture, he graduated from the University of Florence, he has a degree also in green building design from Private University in Rome. And then he applied for Transsolar, and he also, during his study, he became a pizza maker. And so that apparently together these important assets got him a position as a plant engineering firm. So we are very happy to welcome you, and please join me in welcoming Tommaso to Iowa on such a cold day. Thanks, guys.
Does it work? Can you all hear my voice properly? Yes? Great. Okay, so just a second and to finish the story, I actually got hired because I'm a pizza maker. So my very German boss, he saw my curriculum vitae and he said, this is an Italian pizza maker, we have to have you in the company. He didn't need anything else on my CV. He didn't have to know whether I was an architect or an engineer, pizza maker was enough. So that's why I got hired. You know, sometimes life can be easy, let's say. So welcome and thank you, actually, not welcome, thank you for having me here. Just a few words on the company and what we do, just to get you an understanding of the projects I'm going to show and what was our contribution. So we are consultants, so we work with architects, more important or less important architects, doesn't matter. We are in business since 25 years, 4 offices. You see the dots, the blue dots is where we had projects, so mainly Europe, North America, but also all over the world. And the yellow dots is, we have an internal academy. We call students inside our headquarters in Stuttgart. They come from what we call the Miami universe, which we think they are going to have, or they will have the impact on the future. China, Africa, their development will deeply change the future of our planet, also in terms of carbon emissions. And we felt like the responsibility of sharing with them what we have learned, but also understanding from them what still we have to learn, globally speaking. This is our work. Basically, we are kind of trying to connect different expertises within the design process. So we talk about facades, we talk about mechanical system, we talk about structure. Everything is definitely connected to the architects and clearly also together with the client, because the client brings us a challenge, the client has his own agenda, and we need to put all the pieces together until we have basically a building, which is a very complicated system. And we try to do it mainly with design. So the first step, much before the mechanical systems kick in, design is the key for us. And we use to show this picture because, well, to me this is a very sexy design, which at the same time is delivering the message that the design has a purpose, which is efficiency. Everything here is designed to have a certain, aerodynamics with the water and everything, and this is why it is designed this way. This was one of our first design challenge. This is an airport in Bangkok. It's basically a huge volume of air within a PTFE foil, which is just a very thin foil. And the client wanted to have the space, the architect wanted to have the space, they designed it, then they called a mechanical engineer who said, fine, you give me this big volume, I give you a big machine which is going to condition the entire volume. They did the math, they did the costs in terms of capital costs, and the client said, no, I'm not going to do that. So they called us and they said, can you fix it in a way? Can you kind of fix this design in a way? And we said, okay, what is the first contradiction of this design if you combine it with conditioning the entire volume of air? People are here, not here. So we said, we need to condition the bottom, we don't want to condition the top. So we designed the space properly evaluating the performance of the PTFE foil. So what do we need to achieve in terms of passive performance? And then we said we go with the radiant floor where people are. We mainly try to use stratification of air and we keep the bottom cold and the top very hot. This allowed us basically to condition only 1/3 of the volume, and so we basically took the original mechanical system, we squeezed it down by a factor of 1/3, and that was also the capital cost reduction that we kind of achieved simply by design, nothing more. Another design challenge was this building. This design challenge comes from the architect, who is Sana, and he said, I want to have a very thin concrete wall for my embedded. I don't want to have insulation. We can discuss whether this makes sense or not. We can discuss whether it is a right design question, but this is the challenge we got. And the reason why I'm showing this one is because every project has its own identity, and this is the right project for me to show what is a local identity, something that comes from the side, and it's very specific to the project. There was a mine, a coal mine, very close to this building, and since in Germany, now they are reopening that, by the way, because Germany is switching, is closing nuclear, luckily. Unfortunately, they are balancing out with reopening the coal mines. And 20 years ago, these mines was off, but they needed to pump water out to allow, in the future, which is today, to reopen it. So they were pumping constantly water out of this mine, which was very high temperature water, and throwing it into a river close to it. So we said, hey, why don't we take this energy that you are pumping out anyway, so we call the municipality, why don't we pump this water into the wall, and then we throw it into the river. Doing this is an infrared picture from inside, allowed us to keep the walls very warm, because at the end of the day you need thermal insulation for two reasons. You want to decrease the energy demand of the building, and you want to keep the building warm inside, otherwise very cold surfaces around you, they're not going to be comfortable. And we had both, because we had waste energy, so we are wasting energy just in another way, putting it into a wall, and we are keeping it warm inside. Now, the reason why I said, is this a good reason to do it, is because maybe we could have used this energy in a better way, but this project was actually calling to use this waste energy, and so we did. So with a bit of creativity, we can achieve and solve sometimes design problems or challenges just looking at what we have around us. This is Master City, this is a master plan scale, and the challenge here was to build a carbon neutral city in the desert. And we said the first thing you have to do is to design the city in a way that the shape of the city, the canyon, the streets, they are increasing comfort within the canyon of the streets, so the pedestrian level, without any additional energy. So simply by shaping the street in a certain way, you reach a certain performance. You look at this picture is Abu Dhabi, which is exactly the opposite. Abu Dhabi is saying, hey, I take New York and I bring it into the desert, because
It sounds like a very cool design, and this is the result. It's totally disconnected from the local identity of the climate, and then you end up with these very wide streets with 6 lanes, and the temperature of the asphalt can reach under 35 Fahrenheit, and you are supposed to cross the street just by walking. And nobody does it. They take an SUV to go from here to here, which is good condition. Masdar, just having a higher density, can keep a 90 Fahrenheit passively instead of under 35, which is still very high, but you can see the delta. This is just reached by design, by putting together a team which thinks, okay, if I have this deep, this width of the street, then I can improve the outdoor comfort within the city just by design. Why do we do this? The ultimate goal of this is that we have, for 2050, reached carbon neutrality. And for we, I can say definitely Europe, the planet, someone is jumping in and out the Paris Agreement, but this should be what we are aiming for 2050, and this is why we are doing it. Again, this is a European statistics. I'm sorry, I'm bringing these numbers which are the same, very similar to the US. The trend is that one. This is the building industry, is counting a lot, 36% of the overall CO2 emissions. However, what we recognize is that architecture or buildings which have in the back of their design process climate engineering, which is not only us, clearly, it's only a fraction of the overall building industry. So let's keep this in mind. Residential buildings, which are very much driving this 36%, usually are not designed to reach a certain very high performance. So we are basically doing this in this scenario, and we are very much aware about it, but this is all what can be offered. We do it baby steps, and we should all give a contribution to it. So this is more or less what we do. The title I wanted to give to this talk is Sufficiency Before Efficiency, which is nobody understands this title, so probably I should change it, but I'm trying to be provocative. We always think, well, if we are very efficient, that's it. It's not true. It's like recycling, It's like, well, I can use plastic bag anyway, this is going to be recycled. It's the wrong approach. We need to reduce before we recycle, as well as we need to reduce the expectations out of the building before we make it efficient. So I try to build this, also for myself, this narrative. Insulation in a building is probably the most important technology advancement we found in the last 30 years. Insulation made a big difference. It's cutting the energy demand of the building. However, and this is just an information in Germany at least, almost 50% of the current building stock was built after the war with no insulation. Insulation comes basically after the 90s, so only part of the buildings are actually insulated. We have a huge building stock which needs to be refurbished and upgraded. And the same in the US. Technology also made a big step. So if you look at 2000, the performance, which is also the heat release within a space, but it's the efficiency of a desktop was this number here, whatever unit of measure you want to have. And now a laptop goes down 80%. So it's a big jump in efficiency. And this is the result. We are doing better. This is again Germany. This was before 1995. The energy is definitely going down. What do you notice? And I'm very happy if someone wants to answer this question, so it's not a theoretical question. If you look at the breakdown of energy, heating, hot water, building services, domestic power, what do you notice in this trend? What is not changing? Domestic power. Didn't we say the efficiency is like bringing us to an 80% reduction? Well, it's true. So why is not changing? Because now we have 5 laptops per person. So, well, yeah, if you go 5 by 20, you go down to 100% under what? So let's think about it. Is it sufficient to have one laptop, or do we want to have 5 per person? Overall, and this is the ultimate goal, if we look globally, this is the greenhouse gas concentration pathways, which means the red line is the CO2 equivalent in ppm into the air, so it's the amount of CO2 contributing into the air. If we do nothing, this is the trend from today, basically, to 2100, which we definitely don't want to have. We cannot go up there. And those are different trends depending on when we stop producing CO2, what is going to happen in the next year. But this is what will happen if we do nothing, or if we keep doing what we are doing now. So it seems that efficiency is not enough. We gain efficiency, we are still increasing CO2 emissions. Of course, as I said, the building industry is a portion of the pie, but it's still giving a big contribution. And this word efficiency is not only for buildings, it's also lifestyle. The 5 laptops per person is a lifestyle. Do we need that? Manitoba Hydro is one of probably our most famous buildings. The architect is KPMG, so they are the designers. This is the energy demand we get. This is the energy demand of a current Canadian building. So it's a big jump from 600 to 90 kilowatt hour per square meter per year. This is a great example of integrated design. They did an internal competition inside KPMG, 1 year long, paid by the client, which was very driven. I pay you internally to have a competition. They divided the whole firm into 12 teams, and then we helped them deciding what was the most efficient design, which was, at the end of the day, those 3, they were the finalists, and then this one was the winner. And then we built it. I don't want to talk about this because it will take at least a couple of days. I'm still learning something new every day. I talk about this building, I don't know why. It has everything, which is good and bad at the same time. Do we really need to have everything here? I don't know. But the main concept is that we had a chimney which is used in 2 ways. In winter, the air from the offices goes down, so there is a fan pushing the air down, gets recovered in this point, and the heat which is recovered is then pushed back into this winter garden, and then it's basically this loop here. Air comes into the winter garden, offices push down, recovery up. In summer, it's the other way around. Air enters in and goes up by natural ventilation. The challenge here is Winnipeg is cold. How do we do natural ventilation in Winnipeg? And this was the solution. Winter garden, south facing, a chimney which extract the air naturally in summer. So again, briefly, this is a section of the winter garden. This is how basically it works the space. We supply the air in the floor. We have a radiant ceiling. We have a double facade which preheats the air. So all measurements which possibly reduce the energy demand of the building. However, we still have a pretty high amount of mechanical systems inside. I love this picture because this is the picture from inside the winter garden and tells how actually the space which is used for the mechanics of the building, for the mechanical systems, is also used for people. So we always try to integrate those 2 pieces together. You see people doing yoga inside the winter garden, which we use to preheat the air to support the mechanical systems. The green line is what we simulated at the beginning of the design process. We did the certification with this number, etc. We started the building 2010, this was the energy demand, almost doubled. The mechanical systems, which were designed by us, clearly in the process of being designed and being constructed, mechanical systems are complicated. We basically used 2 years to fine-tune everything. And again, the client paid us, and I want to stress on this. The client is monitoring this building. It was very interested not only in having a good and well-designed building, but a well-functioning building. It took us 2 years to fine-tune all the mechanical system to get the point which we were simulating. Sometimes the heat recovery was not working, sometimes a heat pump was just constructed in the other way around, and so on and so on. So the more mechanical systems we have, the more we need to keep track of what they're actually doing, because sometimes we don't see what is happening, and it's there that the energy basically flows. So the question is, how can the notion of sufficiency support a design process towards out of the ordinary building, because this is what we need to design in the building industry, out of the ordinary building, with a positive impact on the environment. Not negative, but positive. A building needs to create an experience, first of all, for the users, for the city, for whatever it is, and needs to interact also with the environment without sucking too much out of it. So it needs to give back somehow. What do we actually need? So this is another project. This is Ricola. Ricola, for who doesn't know, they basically do this very tasty candies with herbs, which needs to be kept within storage like this one, with very strict conditions in terms of humidity. If they are too humid, then the candy basically doesn't taste good. And so there is a very strict, like in museum, it's a very strict indoor conditions. This is the climate in Basel. So basically you see this is outdoor temperature, and this is humidity outside in grams per kilograms. Every dot is 1 hour of the year. So basically the temperature are ranging between 15 Fahrenheit and 100 Fahrenheit, and it's a pretty dry environment. It's not particularly humid in a way. The design challenge was to have a low carbon dehumidification, because again, these herbs were supposed to be kept very dry within the space. And the hypothesis is that, listen carefully now, in order to do that, we don't need thermal insulation. Thermal insulation in the world is not so important, which is exactly the opposite of what I was saying before. So this is how it looks like from the inside. And we decided to use ground earth. We simulated it. Ground earth has the capacity of dehumidifying the air naturally in a way that the mechanical system was able to do it much less. So the material itself was doing it instead of the mechanical system. So we said, let's put all the pieces together. We have an energy demand coming from mechanical systems, but we also have a passive performance of the walls. If we don't use ground earth, which is this green line here, this is basically carbon emissions after 100 years of the building. If we use ground earth, this is the line. If we use a sandwich wall, this is the line, the blue, the purple line. If we use a limestone facade, which has a much more insulation, which has a much higher thermal performance, this is the curve. So they all look more or less the same. But there is a difference. That the limestone facade needs to be replaced every 30 years. A sandwich wall needs to be replaced every 25 years. A round earth, it can be certified for 100 years. If you bring this variable in, you see, even if the limestone facade is much more efficient because it has insulation, so much better than round earth, at the end of 100 years, it produces much more carbon emissions than a round earth. So we went to the municipality and we said, you're giving me a regulation which asks me to put insulation, but I tell you, it's not good. And then the municipality said, okay, you can build this building because you prove that in this specific case, you don't need thermal insulation. So again, in this specific context, in order to provide the interior target condition, higher thermal transmissions don't necessarily lead to higher carbon emissions. We don't need, in this case, insulation. It is sufficient not to have insulation. And this is another building which we opened 5 months ago or so, which is Alnatura headquarters. We are in Germany, very close to Munich and Stuttgart. So the south of Germany. The This is the client. So Alnatura, it's basically a supermarket selling only bio products. So it is very important for them, especially for their headquarters, to keep this vision within the building. It's also marketing reason. So they came to us with the architect and they said, we wanna send this message with our new headquarters. This is the climate, which is again, it's not extreme, it's pretty mild. The summer doesn't get too hot, winter gets pretty chill, but it's not humid. It's still again pretty dry, but not too dry. So, and the design challenge was to build a low carbon emissions building. So the entire building, not only humidification as before, but the entire building was supposed to be low carbon. So the hypothesis is that to do that and still provide environmental quality, so happy people, comfortable people inside, we need to have materials with very low embodied energy. There is no need for mechanical ventilation, there is no need for active cooling, and there is no need for active heating. This is what we said to the client. We were super excited. We were like, wait, I need nothing basically. I just need an envelope, fine. This is how it looks like. This is again around low embodied energy, as we said before. We don't need mechanical ventilation. We need a natural ventilation approach, which has as an air inlet a nerve duct. So it's basically a tube, a nerve tube within the ground, which was 80-meter long, with a fan in case there was not enough natural pressure inside, so there was a kind of mechanical redundancy inside. And then we simply took the air from the earth duct, supplied the air into the space, and then exhausted the air from an atrium, from a skylight, which was basically able to be operable. So it was, we could open the windows on top of the atrium. So this is the inlet, this is the outlet, everything is flowing through naturally, through the space itself. So again, the atrium becomes a space which we use, and we use also for the mechanical system space. And then we started playing a bit with regulations, which is also something that we have to keep in mind. In Germany, this is a conventional mechanically driven building, which says in winter you can never drop below this line, in summer you can never go above this line. But if you have a naturally ventilated building, you can extend this range and you can say, hey, in summer, you can go up to 82 Fahrenheit. Because if you have a naturally ventilated building, your body expects to be warmer. So you say, hey, I am in a naturally ventilated building, it's fine if it's warmer than outside. I have a window, I can control it. There is a psychology behind. And this is also what ushered. This is also the direction of ushered for US and for North American market, which is very important. So we definitely decided to design for 82 Fahrenheit top, which was supporting the idea of no need for cooling, basically. And so we said, okay, fine. Now we have round earth on one side, we have no cooling on the other side. We did a simulation and we said, let's use thermal mass. So you see here different variants. And then let's cool down thermal mass overnight when the space is basically empty. And you see these are the hours, which are basically, it's a measure in Germany, we don't need to go through it, but the more the hours are, and the less is the cooling performance, the passive cooling performance. And we saw that adding thermal mass, so everything is brown, was like adding pieces of thermal mass. So this was a completely light structure, like this one, basically. And then we said, okay, let's have one piece of the ceiling which is rounded, and then all the ceiling and the exterior walls, all the ceiling, the exterior walls, and the exterior walls. And this is the decrease, the passive decrease of these Kelvin hours, which the moment they become green, it means that the regulations was like allowing us to build without cooling inside. So already at this point, only 60% of thermal mass was allowing us to keep out any mechanical cooling out of the building, still keeping off. said, okay, what happens to winter? We had this no heating. So we said, we have solar gates. We played a bit on how many windows do we need to keep in solar gates. Then we have internal gates, which are our laptops. Again, every dot is 1 hour of the year. This is outside temperature. So all those dots, they are hours, operational hours, which are not fulfilling the regulation because you go below this 68 Fahrenheit red line. So we said, well, maybe we need an additional heating. But then we said, what if, instead of having a very efficient laptop, which doesn't release heat within the space, what if we had a very inefficient laptop? And what if we let the laptop running to provide additional heating when needed? So we have a very inefficient laptop, so we go back in 2000, we run this computer much more, so instead of 2,000 hours, 3,000 hours, all the dots that were below the red line, they go up. So we don't need, let's put it this way, we don't need a dedicated active heating system. We can just double use the internal devices and say, hey, maybe there's no one which is using a certain laptop, but you have to do an update. Can you do it when I need heating? Can the BMS find the logic which is allowing me to use what I already have in the space to provide heating without any additional mechanical heating which could go wrong in the next 100 years? This is what we proposed. Well, the client said, I don't think so. So we didn't do it. So we said, fine, that was a nice idea, but anyway, we can kick it out again. At this point, you need to take your ramper wall. You need to add insulation. So look at the consequences of this. Insulation in, you bring hydronic pipes within the wall, which is basically providing the additional heating. And you definitely need this insulation, otherwise the heating provided by this pipe where the hot water is running, the heat is not going the other direction, and we need to have the heating going in this direction. So this was a kind of compromise. We said we have a very nice wall. Let's use at least the wall without bringing in a fan coil. And he was happy. So this is what we provided. We provided this wall as a prefabricated element, and we built it directly on site. We put together the pieces, and then you see this is the overall concept. We have the earth duct here, providing air within the space. The air transferred through this wall into central atrium, goes out. We have our walls, which are 50% transparent because we need solar gates, 50% opaque because we need heating, and that's it. There's nothing else. There's no mechanical system, and there's no cooling system because the air will flow through naturally overnight, cooling down from us. So the takeaway here is, again, considering the context, there is the need for materials with low embodied energy, no need for mechanical ventilation, no need for active cooling, and the client has the need for active heating, which is pretty different than what we said at the beginning. Okay, last project, which we opened 1 month ago. This is in Singapore, and it's a school of design and environment. Now you see the cloud here suddenly goes up compared to the other projects. This is a very hot climate. It's always between 60 and 105 Fahrenheit, and especially has a humidity which is very high. So it's super humid and super hot. Definitely you don't need heating. However, also being super hot is still in between 90 and 100 Fahrenheit, which is not extremely hot. And the design challenge was not about carbon emissions, but was about, it's all related here, but it was about being net zero energy on site. On site is the keyword, which I didn't write. That's the keyword. And the hypothesis again is that we don't necessarily need to go fully mechanical, because when you have a very humid climate, you need to dehumidify the air, and then you definitely need the mechanical ventilation. A conventional approach would call for a fully air-driven system where the air is very dry in a way to keep it dry inside. So the hypothesis is that let's keep this mechanical approach, or reduce at the minimum this mechanical approach. Now, this is the same cloud I showed you before, but it's not. Let's say I changed the unit of measure to give it an understanding, or a better understanding. So basically now we are switching into a unit of measure which is called predicted mean value. And what you have to know to follow this is that you just need to be between this range. Green and slightly red means that it's good. This is where you want to be. So this is, again, every dot is 1 hour of the year. This is outdoor temperature. This is indoor temperature. Everything is very much red. So for 100% of the year, if you are dressed like in winter, and you will see why I'm saying that, if you are well, let's say, if you are not properly dressed and you are under the sun in Singapore, you always feel not comfortable. Clearly. If you are shaded, you kind of feel better. So for 10% of the year, you are comfortable. If you dress up properly, you definitely make a difference. And you go up at, whatever, 40-50% of the year, you are comfortable. If you kind of find a spot with wind, then for almost 90% of the year, you are comfortable. I did nothing. I just said, dress properly, find a spot with wind and shade. Nothing else. So we said, we need to do the same for this building. We need to create a shade. We need to create a wind through the building. And we need to suggest the users to dress properly, which is something that probably the users will do anyway in Singapore. At the moment we do this, our mechanical system here will be only used for 8% of the year, which you cannot do simply by making degrees or creating a shade. So from 100% to 8% use of mechanical system simply by doing this. And at that point, you have air movement with fans, you have an operable facade, you have ventilation, and you supply that little amount of air that you need to never exceed 84 Fahrenheit or whatever was the design temperature, I don't remember. And you see the energy demand compared to the reference building, step by step, increasing the envelope, increasing the efficiency of the mechanical systems, which is important, going hybrid, optimizing the design, etc. It goes to this 500 kilowatt hour per square meter per year. The goal was to be carbon neutral on site. If we cover the entire roof, which it was a bit extended, as you see, this roof is going out of the footprint of the building. This is exactly what we needed to produce 500 megawatt hour per year, which was slightly more than the actual consumption. So the only way to balance on site was necessarily to do this, because otherwise we didn't have any other space. So if you really wanted to go neutral on site, the idea of cutting the mechanical system was a must. And this is how it looks like at the end. You have this not anymore indoor versus outdoor, but it's all mixed up. It's a kind of semi-conditioned space, indoor and outdoor, with this beautiful overhang. People can walk through the spaces, and then the roof was completely covered by PV, because we needed to produce electricity inside. So the takeaway again is that we don't need a fully mechanical ventilation approach. If you design with the right unit of measure, P and V, as I said before, and if you design using the local identity of the space, which is air movement to fight against high humidity. So my conclusions, which I wrote also for myself after putting together this narrative, is that design first needs to be used to provide user experience. So you remember the winter garden of Manitoba Hydro, where people are in, so you enjoy the space. You use them also to increase the performance, not only. And this comes just by design, like master, like designing the street to increase the outdoor performance of the pedestrian level. And then the local identity of a project, we very much like this local identity, which this time I broke into local identity is climate. Its design vision is what the architect or the architects or the mechanical engineers sometimes ask us to do, bring us a challenge. But also the client agenda. Manitoba Hydro has a very clear task, which is we need to send a message to the Canadian building industry. That was the agenda. Support the design team in defining what we actually need. In Amatura, we needed theoretically inefficient desktop. Sufficiency and simplicity lead to robustness and longevity, which is actually what we want to have out of a building. Because the less the mechanical systems, which doesn't need to be zero, we like mechanical systems, efficient mechanical systems. However, the less they are, the less complicated is the understanding of the building, also in terms of operation. We need to think of the building not only design, but also how it is going to be operated. There are going to be people who need to understand it and need to run it. This will lead to a higher efficiency of the building. That's it.
So the question is on the wall, if there are needs for questions from the audience. Yes,
The sauna project you introduced early on, you said that coal mine is opening. What's the solution for the building after they don't have access to the wastewater?
That's a good question. Can I not answer? Before I knew this question was about time, and I don't have the answer because they are discussing to reopen the mine, and then we need to find either another source of energy, which is for free, or we need to add insulation, which may be probably internal insulation, and the architect won't be happy. But that's the way it is. We may also think to add a new system like a solar thermal collector plant to replace that other source of energy. But that's a good question. And it's a drawback of the overall concept, I agree.
and it's a very prominent museum, design museum. All questions answered? Well, I can assure you that Master City actually does work. I was there a while ago, and it is actually cooler than anywhere else in the world without any systems. So if you guys have no more questions, and I hope this was inspiring as for the designer in you, because Tommaso is also an architect. Please thank you again for coming all the way out to Iowa.